allow me to introduce our first speaker, Professor Bryan Low, joining us live from Singapore. Professor Bryan is an associate professor of computer science at the National University of Singapore and the director of AI research at AI Singapore. His research interests include probabilistic and automated machine learning, planning under uncertainty, and multi-agent robot systems. Today, he will be sharing with us his research expertise on learning with less data and automated machine learning. With that, please join me welcoming Professor Bryan Low.
Many thanks for welcoming me to give a talk at your conference. So today, yes, like what she has said, I'll be talking about learning with less, and it will be on automated machine learning and Bayesian optimization. So these are my co-authors of all these works that I'll be presenting to you. So, just a bit of background about what it means to be learning with less data. And later on, I will be emphasizing on one aspect of it, right? So over here on the left, you can see that one way of learning with less data is to perform active learning as opposed to passive learning. In passive learning, what you do is that you're given a bunch of data and you have to train. But in active learning, you are being smart or intelligent in selecting the data that you need, right, for training a model. Now, the second aspect is what we call automated machine learning, specifically that of Bayesian optimization. Now, over for this problem, it's popularized by that of hyperparameter tuning of machine learning models. But however, you're going to see that such a tool, specifically that of Bayesian optimization, right, is good for helping you to figure out the optimum, right, of an unknown objective function. So I'll be elaborating more on that later. Now, active learning, to contrast this to, active learning is about, gathering data to help you to figure out what the unknown target function is, while in Bayesian optimization is to help you to figure out where the optimum is, all right? Then the third topic, right, that involves learning with less data is that of what we call multi-party machine learning. That's the case where suppose you have multiple data owners, for example, different car companies, and they collectively want to learn and fuse, the machine learning models that's running in the cars themselves. Think about trying to predict traffic flow, right, on the road network. However, each of this car company has its own proprietary model that it does not want to share with the other car companies. And because of that, can we actually allow collective learning or fusion of black box models, which can be heterogeneous, right? Now, how can we even incentivize these self-interested car companies to be willing to share data, right? So these are works where we have done some bits of it, but I won't be sharing them here. Instead, I'll be focusing on the topic of Bayesian optimization. It has often been seen in robotics applications. So like I've mentioned just now, in Bayesian optimization, it has been popularized by hyperparameter tuning for deep learning, specifically in this instance of AlphaGo, right? This is the one where the autonomous agent or the AlphaGo agent is pitted against a human player. And at first, it can only win about half the time. But through the use of Bayesian optimization, right, it's able to improve its win rate from half the time to about 2/3 of the time, all right? So that's when this notion of Bayesian optimization became popular. Now, if you want to find out more at a very high level about what Bayesian optimization is, you can read this article. You can even think about trying to optimize the taste, right, of cookies, right, based on the feedback from multiple people who have tried it, all right, and trying to optimize the ingredients to the cookies, okay? Now, in a very recent article in Nature, right, this is the case where they have this robot chemist. Some of you may be aware of this work, right, where, with one of these components of the robot chemist, right, is that of Bayesian optimization. Now, they want to try to find out now what kind of photocatalyst mixtures, right, would be more active than the ones that they themselves have discovered. Now, photocatalysts are materials that help to produce hydrogen from water, right, using light. Okay, and if you try to look through the experimental space, it's 10 variable, and that amounts to about 98 million possible combinations. All right. Now we are trying to find some combination that gives you some kind of optimum. All right. And what they have done is that they have only conducted 688 trials, experimental trials, to be able to figure out a photocatalyst mixture that's 6 times more active than what they themselves can discover. All right. So that's something that has recently appeared in the Nature article. So what exactly is Bayesian optimization? Now, suppose you have some objective function that is unknown to you. It's highly complex. What I mean here is that it is not convex. There's no closed form derivative or expression. And as a result, it rules out gradient-based methods, right? That is so popular. Now, what we want to do, nevertheless, is to figure out what the global optimum of that objective function is. In the case where we're interested in the maximum, then we are trying to figure out the global maximum. All right. Now, since there are no gradient information available, we rely on what we call the zeroth order information. That is very simply sample the unknown function, right? So you're going to get function samples from it. And the key is to be able to obtain or gather observations that are most informative, right? Or provide a lot of information about where the global maximum is, all right? And of course, we hope that we can gather as few observations as possible to help us to figure out what the maximum is, right? And often we are given a very limited sampling budget to help us or to allow us to do that, okay? So what are some of these applications of Bayesian optimization? Like I mentioned previously, in hyperparameter optimization of deep learning models, all right? It can be used, right? Bayesian optimization. So the input would be that of the hyperparameters. For example, the number of layers, the number of hidden units per layer, the learning rate, and the output would be the validation accuracy, for example. Now, we are not able to write down a mathematical expression relating the hyperparameters to the validation accuracy, right? So as a result, treating it like a black box function and trying to optimize it using BO, right, would be a suitable tool here. Now, we can also use it to do active search for hotspots. As you're going to see later, we can use it for policy search for reinforcement learning problems. You're also going to find it that currently we have actually used it for precision agriculture. And I've seen people in material science using it for material design. So on this diagram here, right, it's a very simple illustration. This is actually the ground truth or the function that we are interested in. Of course, this function is not provided to us. It's just shown to you so that you know where the optimum is, which is here. So what you can see is that in Bayesian optimization, it has this notion of what it calls the acquisition function that points at the spot that provides the most amount of information in each iteration. All right. And when it samples there, you're going to see that this white spots start to appear. These are the spots where Bayesian optimization recommends to sample. Okay. So now what you're going to see here is that it has this explore versus exploit, or it tries to optimize this explore versus exploit trade-off. All right. On one hand, it wants to be able to explore the function surface well so that it wouldn't miss a possible location that has an optimum, right? Be it local or global. Now, on the other hand, if it manages to sample a spot, right, where it is close to the optimum, it will try to exploit its knowledge, right, and sample close to it so that it can figure out where the optimum is. So during the whole process where it keeps sampling for new observations, you will see that it goes from explore to exploit, back to explore and exploit, and so on and so forth. All right. Now, what you're going to see next are some of our works, right, in Bayesian optimization. And in the first part of this talk, you're going to see that we try to tackle some of these fundamental issues. Then after that, you'll see that we try to apply it to more complex optimization problems. Now, the first one is what we call multi-fidelity optimization. This is very relevant to the situation where we have the sim to real, right, robot trials. Okay. Now, but I'm going to present here a simple illustration on using it in computer vision. Say, for example, we are interested in the task of hyperparameter tuning of a machine learning model, right? Where you are trying to train this model with 50,000 images. We're trying to figure out what's the optimal hyperparameters for such a convolutional neural net. So every time we train it with 50,000 images, it takes about 3 hours, right? Then out pops the validation accuracy for each hyperparameter setting that we have tried. Now, on the other hand, this is, in my opinion, expensive because every trial is going to require 3 hours. And, what we can do to complement it, right, is this notion of what we call the auxiliary function that we can try to use. Now, in this auxiliary function, we are going to set up another convolutional neural net, okay? But in this round, or in this case, we are going to use much less images, say 5,000, all right? So this is going to train with much less time. It's going to produce validation accuracy that closely mimics this one, which is the original target function that we want to predict, but not with perfect fidelity, right? Not with perfect fidelity, but it has some correlation, okay? So now the question is, should I run the very expensive trial to get myself one sample point, or should I run the much cheaper trial that is noisier, right, than the original one, but it is faster, right, to obtain a result, okay? So, one can think of this in the form of simulations versus real robot trials as well. Each real robot trial is actually very costly. There's a potential danger that the robot will get damaged. On the other hand, you could run as many simulations as possible, all right? So, in an experiment like this, what you'll see is that if we incorporate, right, this auxiliary function that's cheap to evaluate, it actually allows us to improve the convergence rate to the optimum, okay? Now, the next example is what we call the batch Bayesian optimization. One example in the robotic application would be the following, right? Think about trying to figure out where the highest alkalinity, right, would be on a patch of soil, and you are going to deploy a bunch of robots to figure out where it is, okay? Now, the question, of course, is whether you can coordinate these robots in their paths so that they can very quickly find out where would be the spot with the highest alkalinity, okay? And now in this line of work, this is what we call the batch mode Bayesian optimization, where you need to coordinate a batch of inputs so that in every round, they don't waste their effort sampling the same location, okay? So very useful in multi-robot active search, especially for hotspots, all right? Okay, now in any optimization problem, we always care about whether it will go into high-dimensional problems. And so in this case, Bayesian optimization, traditionally, it is very good for problems where you can handle like tens to hundreds of input parameters. Now, in this line of work, what we have shown is that, in fact, we can scale it up to about 9,000 input parameters or dimensions, right, through the use of what we call the additive structure. And we can apply this to problems where it involves multiple controllers, like that of the toll booths, right, where we are trying to control the prices so that the overall flow of traffic can be maximized, all right? Now, this is an example where, we look at the case of looking ahead. Bayesian optimization traditionally is a greedy algorithm, right? It samples the next location based on what it knows from the past, right? So that it hopes to very quickly get to the optimum. Now, however, is it actually possible for us to look ahead? Now, in this example that you've seen here, right, this is a mobility on demand vehicle like a taxi. Now, the question is whether it can look ahead, right? so that it can very quickly get to the hotspot as compared to the case where it cannot look ahead. So in this line of work, we are able to show that with look ahead, it actually gets to the hotspot faster than that without. What we have done previously, right, to look at some of these fundamental issues, right, going from that of multi-objective, right, Bayesian optimization, where there are different objective functions of different fidelities, right, to batch mode, high dimensional input. Then we go and talk about looking ahead. Now, subsequently, we want to look at whether we can use Bayesian optimization in more complex optimization problems. All right. Now, as an example, when we try to apply it to, say, policy search, right, for reinforcement learning problems, we notice that there are additional auxiliary information that's being made available to us, right? Being made available to us. Let me give you an example from what we call the precision agriculture viewpoint, right? Now, if we want to optimize the environment conditions so that our vegetables are able to grow to the most leafy state, then, every trial that we run, we set some environment conditions and then it grows. After 2 weeks, we stop it, right? We see that it has grown to this state. That will give me one data point. But however, what you have also noticed is that along the way of that 2 weeks, you are able to observe how the vegetables grow, right? Now, if the vegetables are not growing up as fast as you would have expected, then this is a case where we consider it not to be promising. In this case, it makes sense for us to early stop and start a new trial, all right? So this is a case where we can actually apply it to precision agriculture, to hyperparameter optimization, where you have the validation accuracy curve to help you, as well as to policy search. Now, we have also applied it, right, to a situation where it involves multiple agents in the environment that is interacting with each other, right? Think about the case of multi-agent reinforcement learning. Now, what we have tried to incorporate into this line of work is that of the recursive reasoning, right? As an example, think of the case of this adversarial machine learning, where you have an attacker on a trained machine learning model. It's trying to provide, right, some kind of image, and perturbing the image so that the trained model is going to predict the label wrongly or with low accuracy. All right. Now, on the other hand, you also have a defender that tries to unperturb or transform the image to a certain state so that it doesn't predict as badly. Okay. And you can imagine this attacker and defender playing a game, right? Where the attacker tries to compromise the validation accuracy while the defender tries to maintain or preserve its original validation accuracy. Okay. Now, what's interesting, of course, is that because of this game, you can think about the attacker thinking that there is a defender who is trying to defend against it, right? And the defender can also think about the case where there is an attacker, right, that is trying to attack it. And because of that, it became what we call the recursive reasoning formalism, right? Where the attacker thinks that the defender thinks that the attacker would do this. So by incorporating this formalism, it allows us to do optimization in an environment with multiple agents that perform recursive reasoning on each other. All right. Now, for those of you who are interested in the case where you, for example, right, you have the case of multiple robot teams, and each of the team is doing some kind of optimization, and they hope to share the optimization outcomes with each other, right? This is a line of work that will be very useful, where we call it the federated Bayesian optimization. On the other hand, if you're interested in, for example, optimizing the policy parameters, right, of multiple different RL agents, and you want to do some form of federated learning across them, this can be used as well. All right. Now, just now I've looked at the case where we are thinking about the case of having multiple agents or robots sharing optimization outcomes wholeheartedly. But what happens when, for example, each of these agents represents a self-interested company or self-interested robot team, okay? Say in disaster search and rescue. And now, in this case of self-interest, is it still possible to do optimization together? Now, how can we be fair in terms of the optimization outcomes? All right, so this is a line of work that will be useful there. Now, for those of you who want to incorporate, right, the case of, to account for risks, this is a line of work that will be very useful. Now, in this line of work, what happens is that, there will be some kind of inputs, right, to the optimization problem, right, where it cannot be controlled by you, right? This could be what the environment offers, okay? Now, if in such a case where there is some input to the problem where it is not controlled, then it induces a risk, right? It induces a risk of actually poor performance, all right? So this is the part where we look risk concepts from economics called value at risk and conditional value at risk, where we want to keep the risk small. And because of that, if we want to keep the risk small, how can we still find good enough, right, values, which is what we call the value at risk, all right? And this is a line of work that allows you to account for risks. Now, we have also applied this Bayesian optimization, right, to the problem of inverse reinforcement learning, where we want to very quickly identify multiple reward functions that are consistent with the demonstrations of the experts, all right? So in this line of work, you'll see that in Bayesian optimization, after it has identified a reward function, right, it will go on and explore, right, the reward function surface to identify the next one that's consistent with the expert demonstration, all right? Now, I've given you a rough overview, right, starting from what we call the fundamental issues of optimization. And after that, I proceeded to talk about trying to use Bayesian optimization in more complex problems. So, in terms of the application domains, these are the ones, the ones where I've highlighted in green are the ones that we have either done or started to do, all right? And the ones that I have not mentioned previously, right, are things like this, where you can look at the use of Bayesian optimization as well going forward, all right? In fact, there are quite a number of papers that make use of Bayesian optimizations to optimize the robot controller as well, especially useful in the case of optimizing or doing policy search, okay? So I think that's all I have for today. I welcome any questions. Thanks.
Thank you, Anji. This is Eric Ferrand here. Thank you for your super presentation. My question is, are there benchmarking efforts in terms of looking at how all these new methods come in and how maybe older methods, randomized optimization algorithms, even like simulated annealing and all these other methods have been performing, or how they complement each other, of how one comes from the other?
So to answer your question, yes, I think there are some papers that look at whether Bayesian optimization is a tool that can perform in some ways better than, other what I call derivative-free methods, optimization methods, right? For example, evolutionary computation, genetic algorithms. These are some of the other competing methods. Now, Bayesian optimization happens to be a kind of tool that has this additional advantage, right? Where they make use of a model to predict the function surface. And using how uncertain they are about the function surface, they try to exploit this uncertainty to figure out where to explore next. So this is something that, the other methods don't usually exploit. Instead, what they do, for example, in evolutionary computation, would be the case where they put in a huge population of agents or huge population of samples, and trying to figure out where the optimum is. Now, if you do something like this, it will not be very scalable if each of this sample point that you try to put in with a huge population, each of this sample point is going to be expensive to sample. And because of that, I would prefer to use Bayesian optimization where it samples one at a time or a few at a time, right? As opposed to a whole population. All right, I hope I've answered.
Thank you very much for your answer. But another question would be, so when does it all break down?
So
what are the bad news?
So the bad news right now is that, I've alluded to earlier on, Bayesian optimization right now is very powerful when you are only optimizing, say, tens to at most hundreds of input parameters. But when you go into the thousands, the hundreds of thousands, or even millions, this is where not much work has been done to be able to scale up to that level, right? So one of the challenge that we currently face is to be able to scale up Bayesian optimization to very high dimensional, high dimensional input dimension, all right, or high dimensional input. Sorry, yeah. So I think this is the key limitation right now. Yes.
Thank you very much, Professor Bryan.